Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
This is the place where we bring people together in search of the theories that are going to change the world. And today is no exception.
Many listeners of the podcast will know that there's this huge problem in physics, which is the fact that the equations and principles that govern the very, very small, like the Planck scale, the quantum scale, the subatomic scale, are completely unrelated to the equations that govern the universe at the cosmological scale. So we're talking about general relativity here. And this has been a problem in physics basically since the inception of quantum mechanics, since the inception of general relativity, where the smartest minds in the world look at this problem and they just kind of give up hope of ever being able to solve it. And so we've hobbled along and we've come up with models that are progressively more and more refined for being able to determine the nature of the subatomic particles. We have field theories that describe the behavior of all of the particles. We have field theory for gravitation, and yet we're still stuck with this immense tension at the heart of physics, which is how do we bridge the two? And today on the podcast, we have Nassim Haramein, who is the research director at the International Space Federation, who is a really passionate, devoted mathematical physicist who has spent the last 30 years of his life trying to figure out if there is some overarching principle that can be used to rectify this tension between the very, very small and the very, very large. And it seems like he may have figured it out.
So he has this paper which came out 2012, 2013, where he does unify these scales by simply arranging elements of the existing theoretical frameworks. And what's really fascinating is that he thought he'd made a mistake with this paper when he calculated the radius of the proton, and it was off by a fairly significant amount. But over the course of the next decade, scientists actually refined the measurement of the radius of the proton, and they came up with this exact value. And obviously, there's going to be detractors who said, well, he kind of knew about this. There was some inkling of it ahead of time, but it was a very unpopular finding. And that is held up over time. And so, what's really interesting in this conversation is that the quantitative reasoning seems pretty sound. The question then becomes, how does this map onto the actual material structure of what is causing these forces? What's actually causing the atom to do the things it does? Why does it tug on other atoms? Why does the center of the atom stick together? What is going on? And so we search for those by surveying the history, by surveying how Nassim treated these apparently disparate approaches to reality to bring them together.
And we've been waiting for this conversation for a long time. I think the first time we reached out to Nassim was probably like 3 or 4 years ago. I feel like it was early days of the podcast. And so I didn't really know what to expect because Nassim comes with a reputation for being a guy who's kind of out there. But it turns out that he's just really devoted himself into honing the way that he makes this presentation to the point where it's it almost impossible to argue with. And so what we leave on the table at the end of the conversation is really how to go to the next step of mapping these quantitative relationships, this kind of mathematical view of the world onto the mechanical substance that is actually the actor. And Nassim's building technologies. He's got this company that's trying to produce propulsion systems harnessing zero-point energy. But the point is that the guy is really pushing towards something super significant, and it's an amazing conversation. He does a really good job of explaining what he's talking about. He has a super good grasp of the history of both quantum mechanics and of general relativity and of the debates that went into the formulation of these things. We don't manage to quite get into Bohmian mechanics, which is kind of the currently favored replacement for the probabilistic Copenhagen interpretation, but I think we're going to have more conversations. And honestly, if you're into physics and you're into trying to understand how the universe works, this is the conversation for you. You're going to really love it.
And maybe you have a piece of the puzzle that didn't come up today and hasn't come up yet, and you need to share it with the world, or at least you need to share it with your fellow listeners. we have the perfect venue for you because we've started a new segment called Paradigm Drift, where you can sign up for the chance to present your theory of whatever in 60 seconds or less. And of course, you're not going to completely unfold that theory in 60 seconds, but if it makes sense and it's interesting and you can tell us what the problem was that you were solving and how it solves it, maybe we'll bring you back. Maybe eventually you'll find yourself on the podcast explaining all the nitty gritty details. So the next taping of that is going to be on September 5th. That's a Friday night at 7 p.m. Pacific. And, you know, sign up. Maybe you'll get to present. Even if you don't get to present, you can hang out, learn how it works, critique other people's ideas. There's a big Zoom chat. It's a blast. We have live music. It is the lighthearted side of this
The very
program.
serious conversations that we have here.
So maybe we'll get into a deeper, serious conversation if you kill at that, and I would love to hear your ideas. So sign up for Paradigm Drift on September 5th.
The link is in the description down below.
It is indeed. Another link that's down in the description, which we really, really need you to check out, is how we pay for this, how we pay for our time to do this. And it's exclusively through donations by listeners like you. We work directly for you. I don't know if you've noticed, we don't have any sponsors. YouTube slaps some ads on this, whether we like it or not. We don't have any ads. We don't have any sponsors. We just have our patrons over at patreon.com/DemystifySci. If you're one of our patrons, thank you so, so, so much. I cannot thank you enough. I love seeing you guys every Sunday. We get together Sunday mornings at 10 a.m. and chop it up about all of these topics. And so, look, if you're enjoying this, if you enjoy what we do here, you find it valuable, maybe you can chip in for as little as 75 cents a week and become a patron and know that you're making this happen.
Absolutely. I hope that we see you there, and I hope that you enjoy the conversation that follows with Nassim Haramein about the unification of general relativity and quantum mechanics.
The scientific revolution starts now.
The DemystifySci podcast.
Want to see in the dark?
A good analogy I like to use is imagine you were looking at water in your tub and you're taking a bath, you got a rubber ducky, and you're pulling the plug on the tub because you're done, and your little rubber ducky starts orbiting the drain, right? You could say that the rubber ducky is attracted to the drain like a gravitational field. And you could look at the surface of the water and start writing physics on the curvature of the water towards the drain. And you would probably, if you did a good job with the stress energy tensor and with the differential equations, you could probably describe the elasticity of water going towards a drain and describe this water structure like space-time or some fluid dynamics, and you would get the right answers. But you wouldn't be able to tell what actually is making the vortex dynamic that's curving the surface. You're only looking at the surface. And so if you plunged in, if you went down into the water to like try to figure out what it's made of, you would actually find that it's quantized. You would find that it's made out of little particles that we call atoms, and then subatomic particles and so on. And you would think, oh, I have a problem. My equations for the surface curving are not predicting the dynamics of this quantized structure down there that I'm observing. And so I've got this, gap between my equations, and I can't figure out how to join the gap. And so fluids is a really good, or plasma is a really good way or analogy to this, because it really is, and the key to it is clearly that it's not one or the other. In the case of the tub with the water, it's both. And when usually you have a dichotomy or like a problem where you have two possible answers. Typically, the solution is both. The chicken or the egg. It's both. And so
Well,
what would be
one of the problems that seems to have cropped up through the history of physics is that the development of quantum mechanics and the development of relativity from the very inception were not married to one another. And I know that you've done a fair amount of research into the formulation of these theories and the history of physics. And so I wonder if you can paint a picture for people that explains what the state of the art was for quantum mechanics, what the state of the art was for relativity, and why it was so difficult from the get-go to find some way to bridge the two.
yeah. Just to finish the analogy, the solution for your bathtub would be to understand that the collective behaviors at one scale of corpuscular structures of discrete structure, at a larger scale, collective behaviors produce effects, forces that you can observe as curvature on the surface of the water. So, so of course, the water is only one thing, right? And so, okay, so historically, why are we not there? Why? How did that mess up? What happened? Um, so there's two things. Um, we we first tried to describe um, the dynamics of reality as little parts, and then eventually we started to think, well, maybe it's more like a field, especially with the equations that led to um, Maxwell's electromagnetic equations that describe wave functions that are occurring on some kind of ether that he called a luminiferous ether, that was this medium that electromagnetic waves were riding on. And that was inspirational to Einstein, definitely, and others. And it led eventually to this description of space-time. And so I'm like doing like a very broad brushes here because there's many details in between. But on the other hand, you have Max Planck that's trying to figure out the thermodynamics of a black body. So you have this problem in classical equations of the time that are describing the radiation of an object, the electromagnetic emission of an object, a black body, which was called the black body radiation. And there is a catastrophe in the equation that was called that way later, but there was a problem in the equations as they predicted an infinite amount of ultraviolet radiation at high temperature. So the high frequency emission were all over the place. There was equations that were trying to solve this. The Rayleigh-Jean equation, it's not clear if Max Planck was aware of those equations at the time, but he was aware of the problem.
Can we just
and there was a
can we pause for a second and just give people who have just come into this conversation a framework for why black bodies are so important? Because the black body spectrum is basically a spectrum of electromagnetic radiation and power density at various wavelengths that comes from any object. So if you put an object in
Heated object. But yeah, most objects have some heat. All objects, I suppose.
yeah, like I was thinking about this the other day, and it's like there's no object in the universe that doesn't produce a black body spectrum because everything has
That's
at
right.
least some heat associated with it. And so conventionally, I think that the way that it's most obvious for people is, okay, well, if you take a light bulb and you heat it, it produces light of a specific temperature, if it's an incandescent filament. And so like
Or like
that's
lava or something like that. I think it's really something like an iron in a forge or something. It starts to glow when it gets really hot. And the color of that glow
Exactly.
corresponds to
For temperature
a temperature,
and a
and that's what's really
frequency. Yeah.
fascinating. And so they kind of knew that originally, from what I understand. They knew there was a temperature associated with it, and so
Exactly.
that Stefan Wine relation was used to predict various things about the spectrum going forward. Except it made this prediction that there should be this boundless quantity of ultraviolet radiation that would be emitted, and they quickly realized that wasn't the case, and so their very predictive and useful equation failed at some point. And so in steps Max Planck uh, with his unique solution and the birth of quantum, as far as I can tell.
Yeah, there's more details that are critical. One of them is that they weren't just looking at the collective behavior of an object made out of atoms. They didn't have quite the description of atoms at the time neither. And, they were thinking how from these equations, so they were trying to understand, that's why it's called a black body, right? That it's absorbing photons, and while it's absorbing the electromagnetic field. At the time they didn't have photons yet, that was Einstein later on. And it's emitting electromagnetic fields, and it's so when it's absorbing, what is it emitting? What is the relationship between the absorption and the emission? And all this was like in the works. It was one of the hottest topic at the time, and we're talking about the 1900, like that year, right? And the years prior to that, like maybe a decade prior to that. And so it really was like a hot topic. Everybody's trying to figure it out, because you get this sense that if you can figure that out, you can figure out the structure of the atom itself, the structure of the little emitters, like how are they absorbing and how are they emitting. And they were describing this as little oscillators, and that's really important to understand. And any student that starts learning quantum mechanics will be first introduced to the concept of an oscillator. And um, and that is one of the things that I take offense to is the way it's introduced in physics classes to young students. It's usually introduced as either a pendulum or a spring with a weight on it that's oscillating. And that's really not what those guys were thinking about when they were thinking of an oscillator at the time. And it's certainly not what, if you're trying to understand the ontological nature of the universe, of an oscillator, which is everything is oscillating, everything, as you were saying, Anastasia, everything is like, emitting and receiving and so on. And so there is always a dynamic. And if you understand this dynamic, then you would understand the dynamic of everything. That was definitely the goal. And so when they were looking at this, they were solving the equation, and there was some practical motivations as well. Max Planck had been hired to improve on the light bulb and make better filaments and so on. So there was some practical applications as well. And so he was trying to figure out how to make the oscillator, the little cavity. So it was described as a cavity. It was even built as a cavity. They were making these little balls that they painted black, or that they put soot on it, that was so that it would absorb heat, and then with a little hole, and then try to measure the electromagnetic radiation coming out from it. And so he was describing this oscillator, and he figured out that if he put this fudge factor in the equation of the time describing this oscillator, he would get the right answer. And he really didn't like that approach. He didn't like that approach. He didn't think it was great, but that's all he could come up with.
This is
And
the H, the quantum of action.
exactly, it became the quantum of action with Dirac when because the equations show that H was always associated with 2 pi, so then it became H bar, and then it was a quantum of angular momentum or a quantum of action. And so basically, he got the right answer. He published it. He wasn't happy with it because it said something weird about the electromagnetic field. It said that the emission of the little oscillator was in packets, in quantas of energy. And that was the beginning of quantum mechanics. And he didn't think that was right. He thought that's got to be wrong. He tried to make his theory more classical. And improve on it. It took him a while, and he published a second theory where he tried to make at least the absorption continuous and the emission in packets. And so he tried to make it more classical. And that was the theory that really kind of threw everything for a spin, literally, because it predicted something. It gave the correct answer. You could get back to the first solution he had found, which was being verified in laboratory and was showing that was the right answer and everything. But he, when he was calculating the internal energy of the system, he was finding that internal energy that he was treating classically at 0 Kelvin, which is, Anastasia, this is where it would stop emitting, right? That would be that thing in the universe that would not emit. Well, instead of
that no one's ever seen
it,
before, right? It's sort of a idealized form. That's not
idealized concept.
It's not happening.
But as you got towards 0, you ended up with a divergence in the equation, which said that you can't actually stop anything from oscillating. And not only can you not stop anything from oscillating, you end up with an infinite amount of energy at 0 Kelvin, an infinite amount of jiggle internally to the oscillator. And he called that 0-point energy.
Interesting. Can we go back to your disagreement with the concept, like with this quantum oscillator idea?
Oh, the disagreement is not that it's a bad idea to do a quantum oscillator. Sorry, I didn't finish that part. I'm sorry.
You're good.
It's that when you teach, it's so critical that we get the right visuals in our mind. It's so critical that when we do an analogy, we don't end up with the wrong visuals in our mind, because then we can't write the right physics if we have the wrong visuals. And so when they were describing oscillator, they were describing something that's spinning, that has angular momentum, that's orbiting, not a spring with a weight on the end. The universe is not making spring with weights on the end. It's not ontologically correct. Like we can, I guess it does after it's made the human, and then the human make the spring and put the weight on the end. But fundamentally, atoms are most likely not springs with weights on the end. So as soon as you do that, although the mathematics are, 1-to-1, correct, comparable, like it's equal, you have the wrong visuals.
I see. And so the challenge is that when we're talking about, say, an electromagnetic system, we're talking about oscillations in the polarity of the circuit, essentially, or the polarity of the electric field, ultimately. And so when we get into quantum wave functions, now we get into like very high level abstractions where the oscillation is in the actual quantum field itself, and that has, you know, imaginary components, and it just gets very bizarre because what's oscillating is an abstract quantity at that point, and it's like, what in the world are we talking about?
Exactly. It becomes completely esoteric, which is one of the hallmark of quantum mechanics, and it becomes a significant issue in terms of actually understanding the fundamental mechanics that would give you the key to unify with general relativity, with the structure of space-time, with the curvature of space-time. It's like you're in your bath and you've got the wrong idea of what's making the vortex in the middle. You're not realizing it's the collective behavior of all the particles in the water that's making the vortex. You're thinking it's something completely different. And since you can't put your finger on it, you can't figure out what it is, then you can't unify to the curvature you're seeing at a larger scale. And that's the other problem in physics, is that we tend to write physics at a very specific scale. We don't necessarily, think in terms of global behaviors. We don't think in terms of collective behaviors. The first thing we do is we isolate the system, right? We assume it's in flat space-time, right? We assume that there's nothing else in the universe that's acting on this thing. And now we're going to do our math. And it's usable and it's practical for certain purposes. But if you're trying to understand the physics of the universe, you've got a serious issue, right?
It seems like the problem too is like, it's not so much that people do that, because the computation becomes sort of intractable when you start adding in, you know, pieces of the puzzle that aren't directly part of what you're looking at or studying. The problem is when you confuse your isolated representation for physical reality itself, which is almost unendingly complex. And like you said, there are always other atoms around, and there are interactions that you can't account for. And so it seems like the confusion of the ideal for the reality is where things start to go off the rails, and people start defending the idealization over the possibility that there's factors they can't see.
So this leads me to unknowingly, I think, well, okay, so this is interesting, because if you look at where this starts with the ultraviolet catastrophe. So you have an equation that predicts that towards the ultraviolet end of the spectrum, you should be getting infinite energies out of your black body. And everybody's looking at it and they're like, well, that's obviously not correct. And so somebody, Planck, has to come around and he has to propose a modification to the way that the equation is parameterized in order to resolve that problem. But then it seems like he arrives at the exact same problem at a lower scale, because then when he hits the limit of temperature in the equation, all of the sudden he's getting infinite energies. And so is that not a
one infinity for another?
Yeah. And so I'm like, is that
very good?
Trading infinities.
Is that accurate? Is that just some artifact of the way that the equation is parameterized, and there needs to be some, like, you know, Planck prime?
We're gonna discuss that in detail, but I'm just gonna give it a brush idea.
Yeah, do it.
Is we can't avoid infinities. They're everywhere. They're everywhere in physics, and maybe instead of avoiding them, we should try to understand them, which is something that Cantor did, with his infinite amount of infinities and so on. And the key to understanding infinities is to understand that they're related to finite boundary structures, like their relationship to it. And that means we have to write physics in scales, meaning we have to understand relationship between scales. If we avoid relationship between scales, then we're not gonna get it. And you know how many scaling laws there's in physics? There's a few. It's one that from Rees and Carr that was published in Nature in the 79. That was remarkable. That is showing very clear relationship, like fundamental relationship between scales from the proton scale to the universal scale. And you had Paul Dirac that with the large number hypothesis that did, that was told he was doing numerology. This like really, really important work in understanding scales, like just pattern recognition. Like let's go back to our bath. Like if we could see a pattern recognition between the particles that are all co-moving and the surface of the water curving, we would have a chance to understand how they relate to each other. But if we don't do physics of scales, then it's not possible. So going back to infinity, I don't mean to cut you off. I'm excited about this stuff. There's a part of what Max Planck did that was mostly ignored until actually recently, and generally it's still considered very fringe and unacceptable by scientists, famous physicists, famous YouTube physicists. I'm not gonna say who, that think that it's invalid. So one thing that was the result of all this exploration, but that started before Max Planck, is that it was noticed that if you put the constants together, including h bar, so g, gravitational constant, the speed of light, h bar, and you put those things together, you get units. You get length, you get mass, you get forces, you get energy, you get all these things come out that are just a relationship of fundamental constants that we measure in our universe. And that should have been, and still should be, a very important hint about how to scale in the universe, because clearly, if these constants are real, and what we're measuring for the constant of gravity and the speed of light and h bar are real, then their relationship predicts like a pixel size. It predicts a certain boundary condition that's defined by the speed of light that says at that speed you're curving space-time. And the opposition to that is Lorentz contraction, and it's not a valid opposition. It really isn't, because it assumes flat space-time, and it assumes that, but if the thing is going at c, then it should contract. It could continue to contract. There shouldn't be a limit there. And it's like, well, it's going at c, but it's in space-time, and so you have to consider what it's doing in terms of energy in space-time, and when it does that, it pinches space-time. And this is Wheeler, Geon, and quantum foam, and that was ignored as well.
Okay, so let's go back a little bit, because I think that we've kind of jumped a section of the story, because we have Planck, we have the quantum of action, which is dealing with the very, very small, and then we also have the emergence of relativity and space-time that's dealing with the very, very big and the very, very fast. And so
Right.
let's unpack that a little bit, and then maybe we can try to lay out the tension that appears between those two views of the world right from the get-go.
Okay, so just, it's a piece of information that's important for the viewer, for them to be able to follow us to the next step. Okay, so I just want to finish on the 0-point energy that Max Planck found. This means that space-time, or some kind of dynamics of electromagnetic fields, these are electromagnetic computations, right? the electromagnetic field at the very small scale is oscillating in an incredible amount of energy. There's an incredible amount of energy oscillating. Whether it's infinite or not is kind of not really relevant right now. But there is energy there, and experiments of the time are able to confirm all the experiments throughout the decades after, able to confirm, yes, there is oscillation even at very low temperature. We see 0-point energy acting on the electron. We see it. We can measure it in the Casimir effect. There's all kinds of ways we know it's there. So on the other side, I'm sorry, I just wanted to finish on that. And then on the other side, you have Einstein that's looking at the equations of James Clerk Maxwell, and that is thinking that there must be a correspondence to gravitation. And that correspondence, and I'm going to skip details again, is he has to like bring it in to special relativity. Like he's already written special relativity. He's got E equals mc square, but in E equals mc squared there's no G. And so he's trying to figure out, okay, so how is this field interactions between particles that we call gravity, between objects we call gravity, is like being transmitted? How is the interaction occurring? And he's thinking maybe there's something like the electromagnetic field that's interacting with the particle, which is interacting with the objects in the space, that's making the effect appear, but that is not part of the thing themselves. That's outside the thing. The thing is making this thing happen, this curvature. And so he writes the equations for general relativity. And here, like, there's a lot we could talk about, but let's just generally say that these equations are really kind of fluid dynamics equations. They're describing, the water in your tub. And here again, I have an objection to the typical analogy, which is like a ball on a trampoline that has another ball coming towards it, right? It kind of works, but it's so much more accurate to describe it in terms of visualization, to describe it as a flow of space-time towards the center of an object. And literally a flow of space-time towards the center of an object. And that produced singularity in the middle, but
I mean,
that is what
I think it's
says.
really hard for people to imagine a flow of space-time because space-time isn't a substance, it's a dynamic. Like you have already a moving picture and you're talking about a movie moving now because there's already time in that abstraction. Do you see what I'm saying? It's very hard to
Yes.
picture the
Yeah.
motion of a motion. Like your fundamental
but
substance is a motion to begin with.
yeah. Okay. Okay, let's unpack that in a little bit because you threw time in there.
Well, you
And
said space-time, not me.
yeah, I understand. I agree. No, it's correct. I'm not debating that. I'm just saying if you actually rigorously look at space-time in those equations, time is not a dimension of time. It's not it's not an arrow of time. Time in those equations is another dimension of space, but it's a dimension of space that's interacting with the position of the body that you're studying. So it's the light bouncing in the space between the body that's orbiting and the body that's producing the curvature. And so it's not really, it's called time, but it gives, again, kind of the wrong visuals of if it, and you can support what I'm saying just by looking at the units, which are typically removed. That's another thing that should never be done in physics, when we just do h bar equals g equal c equals 1, right? Like, that should never happen. We should never remove the units. All of physics is about the units. You cannot remove but when you put the units in, you realize actually the time dimension in the 4 vectors is actually a velocity. It's movement in the space. So it's not quite time, but and so basically, when you I know it's more difficult to think about it this way, and certainly Einstein eventually came to that conclusion. He said general relativity is irrelevant or is inconsistent without an ether, because he needed some kind of flow, he needed some kind of pressure, he needed.
I guess that's what I'm pointing at, like, more than anything, is just that, if you're looking for the most rational and easy to understand visual, then you have a statically conceived substance that's in motion, right? So, if I want to visualize anything in my room right now, I have to imagine the thing first statically, and then I have to apply motion to it, which is really just changing its position with respect to everything else in the room. And so, what is that stuff that's flowing towards the center of this gravitational vortex? What is the stuff? What happened to the ether here?
Yeah, but the difference between the thing in your room that you're observing and that you're applying motion to, and these equations, is that you have a source. So you have an interaction between two things that are influencing, right? So it's more complex than just saying, okay, assuming my rubber ducky is alone in the universe and I'm in flat space. It's different than that. It's actually interaction between curvatures. So,
well, it's interesting because, okay, so if you have that an object that is exerting gravitational force is creating this vortex of space-time, the vortex requires a drain, right? So it's like in the tub, there's no vortex until you open up this empty space, and then things drain into it. And so when we're talking about space-time as a vortex, is there some conception of the system that is creating the drain?
Yeah. So be more precise. Be more precise when you describe pulling the plug. What's actually making the vorticular dynamics of the water?
Man, you're going to test
Gravity.
my physics. Yeah, like gravity, Coriolis forces.
Yeah, gravity is involved, but fundamentally, you have a gradient. You have a change in density, right, between the air in the drain and the water in your tub. There's water going down and there's air coming out, right? And so you have a gradient density change, which you can observe in the atmosphere, that makes hurricanes, that makes, small gradient of a few degrees between the surface of the water and the air will produce hurricanes with like millions of tons of water flying around and lightning and all this stuff. And so the concept of a gradient brings you directly to the concept of scale. But go ahead.
Well,
I can see you have an objection.
All right. Well, it's not even an objection. It's just that I have a hard time the thing that I was thinking of is I was like, well, if you go into the ISS and you have a tub and you pull the plug, you're not going to get a vortex. And so the gradient itself is insufficient because you have to have some kind of gravitational potential that wants to pull that water down.
Same for the hurricane.
Same for the hurricane, yeah. And so I guess the thing that I get stuck on is like there has to be some driver. That's
Yeah, like
exactly right.
what is the source of that pull?
Right. Well, in this case, we're talking about the thing that's making the gravity, right? So we're talking about the space-time structure that makes the gravity in the first place, that makes the energy that produces the effect.
And this is
Meaning,
kind of a sticking point, right? Because like and I don't expect you necessarily to have the answer to this. I think that this is like a foundational problem when you start, because when we talk about forces, we talk about forces as kind of these idealized pre-existing dynamics. And so there is a body that has produced a gravitational force. But I think that
yeah,
it is possible to go one step farther to ask, why does the body produce the gravitational force in the first place? And
right.
I think that that's kind of like a deeper metaphysical question that most of
No, I
physics
don't
doesn't.
think so.
Oh, you don't think so?
I think, no, I don't think so. I think you can actually answer those questions. Absolutely. I absolutely think that's totally answerable. It's just that in order for you to see the whole picture, I gotta develop the picture further
Yeah, it's
for
absolutely that.
you.
Absolutely.
That seems like an honorable goal for the course of what follows.
Yeah, I
We can
agree.
circle back at that and see if we've answered it by the end of this conversation. But yeah,
Right.
Anastia is right. Like
Absolutely.
we're not trying to like put any gotcha questions. Like these are things that we're obsessed with too. Like these
Oh no,
questions are,
absolutely.
yeah, we're really trying to
Yeah.
just figure this out, honestly.
Oh yeah, absolutely. I totally get that. This is why I'm so honored to be on your show.
Uh,
That's why I'm so grateful to be talking to you guys, because I can tell that you guys are going after the truth, and it's not some like, okay, I want to support this or support that for some unknown reason or some egotistic thing, and that's really powerful. Like that's really powerful, and it's actually rare.
hmm.
Hmm.
Everybody's got a little
And
piece of that truth. I feel like that's the fun thing about talking to so many different scientists and thinkers. Is
right,
I feel like everybody has maybe some people have big pieces, but I feel like most people have something to add to that puzzle, and that's honestly why physics is such a intergenerational, like intra-human being project. Like no one has everything. It's just across time and across all these beings, we're figuring it out. So, anyways, that's what we're
right,
trying to do.
right.
But so to get us
Well,
back onto the track of
yeah,
this story, right? So we have
right.
Einstein that puts together the equations that govern the curvature of space-time that produces this attractive relationship. But then we're stuck with this question of like, okay, well, one of our friends, Jim Keller, actually, he's always infinitely amused by this, where he's like, okay, so you have the picture of the bowling ball and the trampoline, and space-time is curved by the mass,
Yeah,
but like
yeah.
the math, it's not the curvature that you're trying to explain, really. Like, in some ways, what you're trying to explain is you're like, how did that thing get heavy enough in the first place to be able to curve the stuff that's
What's
around
pulling
it?
on the bowling ball in the
This
first place?
exactly. This is what really bothered Einstein. He's he said, I got the metric side figured, but the stress energy tensor is like sand in my hands. I can't figure out what do you mean by mass, right? Like you just decided to put a mass, like it's a free parameter, you put the mass. Okay, well, you know uh, that's so it's like, oh, if you ask where does everything comes from, oh, let's start with a miracle, we'll call it the Big Bang, and you could go to church and like you get the same answer. What started the whole thing? Oh, it was God. Like you got about the same amount of information, and so basically, uh, there's dynamics that have to do with infinities, and this is where I was getting at. This is where you cannot avoid fractal structures of infinite potential. You cannot say the universe is going to stop at one spot and it's just not going to go any further.
Mm.
It's not gonna get bigger. It's not going to be in a larger universe, and that larger universe is not going to be in another. You cannot say that stops at one point, or you can't go and say, well, the Planck scale is the smallest thing and nothing else happened. But what you can do is figure out what relates the scales with each other, and then you can write physics knowing that infinities are involved in the dynamics that you're looking at.
Okay, so this
Because
is super fascinating to me because I've been trying to work something out recently. Like, do you know about abstraction layers in computer science?
yeah, I think I know a little bit about it. It's not my field of expertise at all.
Absolutely, and not mine either. And so permit me to put something on the table that maybe I think is relevant to this discussion. Because as you're saying that like we have these different scales, and the different scales have different mathematical relationships that apply to them, and there has to be some principle that allows us to relate these different scales to one another. The way that people build computers is kind of similar to this in the sense that each layer of the technology stack, from the moment that you start to build a semiconductor to assembling them into chips, to discovering the logic that the chips require, to figuring out, the machine code that you have to run in order to standardize that logic across different process. Like every single one of those steps has a particular mathematical relationship to it. And I haven't figured out quite how to link this back to physics, but I think that physics operates at the same level where at each scale you have a set of mathematical operations that work there. And then when you try to go to the next scale, they don't work anymore. Because like in the example of the water in the bathtub, we're talking about the fact that you have multiple layers of organization of the fluid. And at the macro scale, what you see is a vortex of it going down the drain. And that's described by one set of mathematical operations. But if you're trying to understand, let's say, the hydrogen bonds between the water molecules, that's a different set of mathematical operations. And is there some way to go between the mathematical operation that describes the flow of the water in the bathtub to the hydrogen bonding forces, to the covalent bonds, to the structure of the nucleus and the electron and the relationship between them?
Well, okay, so here we're getting to it. And I just want to say the fact that we're grappling with those, thoughts right now is exactly what Einstein was really trying to solve. Okay, so like, don't feel bad that it's not clear, right? It's just, it's been going on for a while. But but you made a big assumption in your description right there. And that assumption is that the dynamics you see in your tub at the large scale is not the same dynamic that's happening at the hydrogen atom scale. Maybe those hydrogen bonds that you're seeing is the same thing that's holding the rubber ducky in orbit in your bath. Maybe there's fluid dynamics of space-time at that scale that are producing those same, holding force. We'll call it confining force. Could be the van der Waals force. Could be the color force, the residual strong force, the color force. Maybe all these confining force that's holding to the center, the thing that's making the drain is that the drain is just fractal all the way down, like that there is drains all the way down.
So it's not turtles all the way down in this model, it's drains all the way down.
Yes, exactly. Exactly. And this is what Einstein and Rosen came up with. This is why Einstein and Rosen wrote that paper in 1935, trying to make point particles little drains that turned out to be wormholes in the structure of space-time. But this is literally what they were trying to do. They were trying to get rid of this point particle infinity issue in quantum mechanics. And because what are they struggling with? They're struggling with scale. They're struggling with how do we get the scale to give us, clear idea across? And Einstein's thinking, this is working great at the cosmological level and everywhere else in the classical world. I'm sure I can apply it to protons, nuclei of atoms, and get the right answer. Now there is the hick that like tripped all of physics out until now. Like this is where it went sideways.
Because
Okay.
they didn't succeed
They
exactly,
missed.
right? They didn't find like a stable way of solving that problem exactly.
They didn't, but they just missed it by one hair. They missed it by one hair, and I would say less than a hair. They missed it by microns of a hair. And
All right.
because there was no straightforward, clear understanding of confining force at the time, and they had no idea that their equation gave the correct answer, but without the correct relationships. Meaning they got the correct answer, but they missed until now. Until me in my van in the 90s, solo climbing every morning and like trying to figure this shit out, going, wait a minute, calculating as I'm like
Oh,
climbing up
dude, you're a
mountains.
climber? I had no idea. We love climbing. That's crazy.
Oh,
You're like literally on
awesome.
cliffs. Where is this at?
Squamish, Canada,
Amazing.
in the Rocky Mountains. Yeah, I was
Hell yeah.
I was a mountain guide. I was a skier. I was like, yeah,
Amazing.
that was my life before.
Nastia's a mountain guide too. I don't know if you knew that. She just got back from a trip actually, which is why we got this nice virus rolling around right now at the house.
But I do think that it's really interesting how spending time in nature and a lot of time, if you have this kind of mind that's oriented towards the questions of fundamental physics, when you spend a lot of time in nature, there's something about just observing the natural world and seeing the patterns that induces you to see that there must be some kind of scale relationship between things. Like, we were at this lake and I was just watching, it was a perfectly smooth lake surface, and there was a rock that was sitting in the water. And it kind of had this weird texture on it. And as I was watching it, I was realizing that as the water undulated around it, it would create these loop currents around it. And I was sitting there for a while and I was just preoccupied by how beautiful it was. And then I was like, oh my God, that looks identical to the coronal loops on the sun. And I don't know what to do with that, right? Because I don't know how to parameterize that mathematically, but it seems so obvious to me after watching it that I'm like, oh my God, it's an interface question. Like, we see these things and it's very hard to tell like what is coming from where, but we see the patterns only in one frame and we're missing some larger context for what's causing it.
Good, very good. And now, I was a ski coach. I was a ski instructor. I was doing all this stuff. Now imagine that the rock that you're seeing is a little ice blob, like a little iceberg, right? It's gonna do the same pattern you're gonna see, but guess what? The thing that looks solid is just a different phase of the thing that looks fluid. It's not two different things. It's one thing. You see this. You see the separation we've made between the field and the crepuscle is artificial, right? If you can scale, you would see that the crepuscle is a dynamic of the field, and that the field at the larger scale is a dynamic of the corpuscles co-moving, orbiting collective behaviors. You see, and then all of a sudden becomes one thing acting at different scale, giving you different sets of information, right?
And so what is the thing that Einstein and Rosen missed by this micron that would have allowed them to see
I'm
it?
afraid we're going to have to unpack lattice QCD, or we're going to at least have to touch on this idea. I know it's mathematically painful, but maybe we can avoid some of the painful pieces and at least orient people towards what the piece of the puzzle was that's been developed in the years since.
Yeah, of course. I think that so what did they miss? So they're trying to deal with these infinities again. and it just happens that they have them in their own equations, meaning Einstein has this problem of infinities in general relativity, which is something that most physicists don't realize. That is that Einstein field equation doesn't make stars, doesn't make galaxies, doesn't make planets, doesn't make the classical world. It doesn't do any of these things. It just makes singularities. Like these equations don't get solved in other ways in which you don't have singularity, where you don't have a black hole. Even the chaos metric, you can avoid somewhat the singularity, but you still have a black hole. And so whenever you use Einstein field equation, you're actually using black holes mathematically, right? Like if you're trying to figure out the orbit of the Earth around the sun, you're making the sun a Schwarzschild black hole, and you're making the Earth a Schwarzschild black hole, and then you're looking at their relationships and you're getting the right answers. But you've made them black holes mathematically.
Like in the sense that they're point sources of the interaction.
Of a mass,
Yeah.
exactly. And this is critical to, figuring out the drain. So Einstein goes into like, well, maybe I can make the drain so I can come up with like the source of the stress energy tensor, the matter that's curving space-time. Maybe that's the drain, right? And so he's trying to make particles with the general relativity equations, and it leads to like he does find a drain, a pipe. It's a wormhole, and it's connecting non-linearly. It's connecting, space-time in such a way that it is non-local, meaning it's could be the mouth could be here and the exit could be there and could be in another universe, right? But it's saying the drain is a wormhole. And actually, if you're very rigorous with Einstein field equations, it basically only predicts a wormhole with a mouth that's a black hole. That's what Einstein equation predicts. And so he's trying to make the proton one of these. He puts the mass of a proton in the equation, and the Schwarzschild solution, R sub s equals 2gm over c squared. It'll give you a radius for the thing, right? And the radius he gets is 10 to the minus 54, which is like 20 orders of magnitude smaller than the Planck, right? And so it's like, this doesn't work. His dream of unifying physics by making classical object just crashes, right?
Because it's basically not strong enough to keep the wormhole open, from what I understand, right?
Exactly.
There isn't enough energy to actually make this a stable conduit to connect it to the rest of the universe, and therefore unify the small with the large.
Right. So are you ready for like the micron hair error they made?
Let's go.
Oh, yes.
It's going to change your world. It was the fact that instead of a radius, they should have looked for the mass, but they had no idea to do that because I noted it right away in the 90s because I was working on this like crazy scaling idea of the universe. And so I had studied the Planck length very, in depth. And so I looked at, if you did that, I did it independently. I realized Einstein had beat me to it. But I realized, well, wait, that is exactly alpha G. And there's no way he could have known, because alpha G, the strong force, the color force, was not discovered. Actually, Yukawa published his paper the same year, but it was not confirmed, and it was very like it's only recently that we can even measure it. And
Tell
so,
people what alpha G is, because this is central to your
okay,
theory.
the alpha G is a fundamental constant in physics that is kind of forgotten. It's in the dust of the closet of physics, and it's the ratio between the gravitational force and the strong force. So it's the ratio of the energy you need from a gravitational force to produce the strong force.
Basically, to hold
Right?
the proton together, right? To hold the nucleons together, right? So it's like if
Again,
you're trying to make an equivalent between gravity and what's holding the nucleus together, if you're trying to make that leap, you have to scale it in this particular way.
that's right. You have to scale it. And he was trying to figure out how, but instead of changing the radius, instead of trying to figure out how small would the proton be if it was a black hole, he had to flip the equation and go, how heavy, how much energy I have to put in the proton for it to become a black hole and stay at that radius that we measure. And if he would have done that, he did that. But if he would have had alpha G, he would have right away noticed it's exact. It's not approximate. I just want to say it's exact. It's exactly the strength of the color force. Like it's exact. It cannot be said. It's exact with the level of accuracy that we can have in physics today.
All right, so I think we have to talk a little bit about QCD to understand what a color force is, and we're going to lose
Right.
some people really quick if we don't. And also the difference between lattice QCD and I guess the earlier version.
Oh, and yeah, well, we can. There was okay. So before we get into QCD, there was at the time some debate of what's holding the nuclei together. Right. This is why Yukawa published that paper. It was a solution which is still stands somewhat today.
This is the strong force, the origin of the strong force.
The origin of the strong force. The color force was not known at the time, but certainly something was holding the nuclei together. Protons are charged; they have an electrostatic charge that's very strong, and they want to repel and they want to go away from each other. They don't want to be stuck together. There's no reason for them to be stuck together unless if there was a force that's holding them together, right? And because nobody noticed, you just got it.
No. Maybe I did just get it. I'm just
Nassi's having a hard time with the Star Wars level of this, I think.
Yeah, it's like there's a force that holds them together, and I'm like, the force has to come from somewhere.
Right. That's where I'm getting at.
Yeah. So I think that I think that I'm leading into where you're going.
Okay. So yeah, but at the time it's like, okay, we got to come up with a force because it's too strong for the proton. It can't be gravity, right? Can't be gravity. It doesn't have enough mass to curve spacetime enough to be gravity. Unknowing that the little drain wormhole of Einstein and Rosen actually give them the answer. Okay? And so basically a whole new branch of physics. There was a little bit of, for a few decades actually, there was a little bit of a battle between the concept of strong gravity, some kind of gravitational field that's stronger than what we experience at the classical level, and this new approach that eventually became QCD. and QED. And the tendency was to abandon classical views at the time in quantum mechanics. We almost have to jump back to quantum mechanics now because, like, in order for me to go into QCD and QED, I have to go back to quantum mechanics. So, but let me just finish on that other part. Let's just make it like really clear and smooth. If Einstein would have made the proton a black hole with the mass necessary that his equation predicts, he would have got the force of the strong force, because the energy required to curve space-time is exactly, not approximately, exactly what we measure. Okay, so let's go into QCD now. And we'll talk about the range of the strong force in a minute, because it has the wrong range at the classical level. I'm acknowledging that. So, but so now if you go back to QC, like so basically, let's go back to QED first. Remember the 0-point energy thing? Okay.
Yep.
Even if Einstein would have figured out that he needed to add that mass, he would have had to find a source for that energy, right? And you might say, but we don't measure that mass. No. What I'm telling you is that we are measuring it. We're calling it the strong force, okay? Because mass and force are interchangeable in quantum mechanics, meaning, this is more your field of expertise. If you take, the nuclei of atoms and you keep adding protons and neutrons, you can't just sum up the mass. The mass is reduced as you grow up. And as you grow the nuclei, you lose mass because it's converted into force. Okay, it's called a mass defect. And so I'm throwing a lot of things in there, but QED, so electromagnetic dynamics of the Planck of the atomic scale. I hope I'm not boring you, and I'm not making it too hard. But it is a little complex.
No. We'll rope it all together in a second. Just follow your train of thought, and then we will do our best to check to make sure we understand after that. We'll bring people along.
So basically, if you, like in the paper I just published, if you actually take rigorously Planck's law, right, the black body radiation laws, and you apply them, and you go on, this little oscillator, like this magic force that you're not keen with, is in there already. Because what's making the oscillator oscillate? Right? Well, in the equations, if you follow them rigorously, it's 0-point energy, meaning the ground state of the oscillator is required for it to be able to oscillate. Otherwise, it dampens. It radiates its energy, Lamnoir radiation. It will dampen, and within billionth of a second after the so-called Big Bang, everything would have disappeared. Like you need the oscillator to keep oscillating. you need it to keep oscillating, and this is where I saw some interviews where you guys were talking, and please don't take this badly. I really
we rarely do. That takes a lot.
You can't hurt us.
Yeah. You guys are talking about how there is no perpetual motion, that like there's no evidence of perpetual motion in nature and all this. And I would challenge you to find something in nature that's not perpetual, right? I would challenge you to find me a proton that has decayed in 13.7 billion years since we've seen protons. Okay, we haven't found one that has decayed so far. All we see is change in phase. We change in relationship. We see phase transitions, right? We see change in relationship of things, but we don't see. I'm gonna say to you, conservation of energy laws and thermodynamics laws are conserved locally, are not conserved locally, but are conserved globally.
That makes sense. I mean,
Okay?
if we treat the universe as a closed system by itself, then yeah, you're not gonna ever. You have nowhere to dissipate that energy to, so everything stays internally. And obviously, electrons seem to keep chugging along. They keep in motion. They have a standard angular momentum. It's there.
And protons, and even protons don't decay whatsoever. And even if you collide them, they reconstitute. It's remarkable, and so on, and so basically, if you look at the equations carefully in quantum mechanics, the current equation, they place 0 point energy to zero. They said basically all the electromagnetic interaction in the field are canceling out, making the ground state. We're only addressing physics above ground state because of everything's canceling out to zero. And when you do that, your equations become commutative. And when equations are commutative for the oscillator is losing energy. It will dampen and die. And so all of a sudden you have a magical oscillator that's like creating reality, just like magic, right?
And so I
And
heard you say this during the Barcelona talk, and the way that I interpreted it was that you were basically saying that you have these oscillators, and the energy for the oscillator is actually fed to them by the ground state motion of the rest of the universe. Is that accurate?
that's right, that all oscillators are interacting, creating the oscillation in each one of them. You have feedback relationship between all, which leads to the drain that is a wormhole. And you have feedback mechanism, information transfer mechanism across scales that's keeping the whole thing going.
So is the
And the
basic
scales
idea
don't
that like
end.
this vacuum energy stuff isn't just like hiding out in the middle of nowhere. It's kind of the collective sum of this low. It's just the residual energy of the entire system, something like that.
Right. And because like the entire system has infinite scale, then your equation is going to end up with an infinity, whether it's in the middle of a black hole or whether it's the energy supply to an oscillator. Like the information or the energy emitted by your oscillator is still in the same field. It's still conserved globally.
Okay, so in this model then, is the drain literally just the tendency of these systems to gradually lose energy through whatever let's say it's analogous to a classical process where there's
Or draw energy
or
from the
draw
Draw
system.
energy
energy from
and
the
lose
system.
energy. It's absorbing and emitting.
Well, like in order for
It's
it to draw energy, it has to lose energy, or you start to get
That's right.
changes to the
Somebody's got to
system.
lose it.
Somebody's got to lose it. And so basically, like
Yeah,
if you have a proton, it's a system that is somehow losing energy over time, and in order to maintain itself, is pulling more in from the universe.
that's right. And from 0 point energy. And so we in this paper I sent you, we do the first thing we do is the correlation functions of the electromagnetic field inside the cavity of the proton to see if we get anything valid. Like, you know what the correlation functions are, right? Like they're equations that tells you how many waves are canceling out and how many waves are creating standing waves of energy. And so you can calculate with these equations in a field of wave interaction with all the modes of interaction. You can calculate. Here's the hic: if you renormalize at the Planck scale, if you say, okay, my Planck scale is my smallest wave, all the other waves, how inside the cavity of the proton, so you have a limit on the larger waves as well, right? Because you're inside the cavity of the proton. How many are going to cancel out and how many are going to be constructive? And when you do that, guess what you get?
The wave
The
function of the
exact
proton.
mass of the proton. Yeah, the exact energy of the proton, the exact mass of the proton. Not approximately, the exact value. Now, just to compare this to QED, okay, currently the mass of the proton is predicted by 1% by the Higgs mechanism. So the Higgs mechanism, with all of its glory, is only able to predict 1% of the mass of the proton. Okay? Well, 1 to 5%, they're unsure because it's not very precise, because all of QED and QCD is curve fitting renormalizations everywhere, new fields. And so what they've done is they sliced the electromagnetic field and they said, okay, for each particle, we're going to have a field. Okay? And now you have quantum field theory and QED. And now you get like this idea that like every field has a particle is carrying a particle, and every particle is carrying a field. And these fields are literally like pulled out of nowhere. Like it's really smoke and mirrors. and so it's self-consistent inside the standard model. It's self-consistent inside the standard model, but applied to the real thing, like the mass of a proton, you're missing 99% of it. Okay. And then the other 99% that's missing is attributed to various mechanism in QCD, in the strong force. So the color force,
like the kinetic and binding energies and things like that.
That's right. Exactly. So it's the gluon field with the quarks that produces the energy from this, for the rest of the mass of the proton. But when you look at these equations, it's hand waving. It really is. It's not fundamental. It's not like it's nowhere close to being a fundamental theory. Any physicist that's honest about it will tell you it's a way to calculate that gives us approximations. We run supercomputers for years that cost billions of dollars to run for these calculations, and at the end of it, we have approximations.
And that's the lattice, by the way. It's like these simulations chop up space-time into these little voxels, essentially. And so the kind of granularity of it is why they call it a lattice.
And it's the correct thing to do, but not with this formalism. Because if you have the formalism that's fundamental, you will find that space-time is chopped up in little bits, and they're called Planck oscillators. Like, but they missed that. They missed that because Einstein and Rosen were not understood. Right?
Pardon the interruption, but I have to ask you for a favor. If you are enjoying this conversation and you have enjoyed other conversations that we have had on this podcast, please come over to patreon.com/DemystifySci. You can donate just 75 cents a week, which is, even in these troubled economic times, not that much for an individual person, but for us, it means that we can eternally keep this podcast going without having to have sponsorships, advertisements, or having some kind of editorial board that we answer to. So come over to patreon.com/DemystifySci and help power the podcast.
I want to moderate what I said because I don't want the physicists to get really upset with me, although I'm used to it. But this idea that the standard model is self-consistent but not really directly related to reality is I mean QCD, for instance, there's this virtual pions that are mediating, and it's based on effective field theory, and effective field theory is just like basically statistical, like curve fitting stuff, and like I said, it's not analytical, it's not fundamental, and most of the energy and resources are going towards these standard model theories, building huge accelerators, colliding proton at faster and faster speeds to get smaller and smaller particle. And nowhere in the literature, other than a few illuminated, like Feynman, mention that there might be a fundamental issue with the idea that you can continue to break protons and get smaller and smaller pieces and get any information about what you're doing. So for instance, when I'm talking about protons, I'm talking about them being very fundamental. And physicists say, well, protons are not fundamental because they're composite from quarks and gluons and all these other particles that like we see when we do accelerators. And I have one, I'm gonna just break paradigms, but I just have one fundamental questions, right? Um, if these particles were fundamentals, the ones you're getting in an accelerator, like I'm crashing two cars together and I'm getting pieces flying everywhere, right? At very high velocity. If these pieces that are coming out could be the eye of the driver, or it could be the boat that was in the carburetor, or whatever, right? If these pieces were fundamental to the things that I'm trying to understand, the thing that I'm trying to probe, wouldn't these pieces be stable? That is, those pieces we get, the longest lasting one lasts 10 to the minus 8 seconds. The shortest one, like the Higgs mechanism, is 10 to minus 25 or something like that of a second. So let's unpack that. Like,
And
so if
even
the
like something
universe,
super fundamental like the neutron, like a free neutron doesn't last very long, right? Like 15 minutes or
that's
something.
right,
So how can
becomes a
that possibly be a
proton.
fundamental building block? It just
It
doesn't compute.
reverts back to something that's fundamental, which is called a proton, which doesn't decay, stays there, doesn't budge. It's a building block. The universe does protons, and when they're done, they stay, right? But those other things, as soon as they're made, they go back to the vacuum. They disappear. They're gone. Their energy, they are not stable in any way, shape, or form. How do we consider that to be fundamental? Either then it's fundamental to the theory that you wrote, right? And the energies that you wrote to find the thing in the first place, right? It's circular and it's self-consistent inside the theory, right? But that doesn't mean you're understanding the universe, or that these things are fundamental to the way the universe is building itself. If I'm trying to understand the ontological nature of the universe, these things are not obviously fundamental to the way the universe builds itself, right?
So that actually answers a question that I had just as we started talking about this, which is that how do you define a fundamental particle versus a not fundamental particle? And I like this idea that it's something that is stable for long periods of time? Because it seems like you do get some piece of information out of taking something that's really stable and crashing it into something else that's really stable, which is that then you're somehow disturbing the surroundings. And so what you see in them is you see these momentary fluctuations, but the momentary fluctuations seem like they might be inherently external, because what you've done is you've smashed these two things together. That energy goes out into the surrounding, you can call it the field, you can call it the medium, whatever, but what you're really observing is you're observing the mechanical dynamics of something that is being disturbed by the collision.
Yeah, and you might say, well, I see those in nature as well. And it's like, yeah, you will see protons, you will see particle creation in nature in very high energy environment and all this. But that doesn't mean they're fundamental. That doesn't. If they were, they would stick around. They would make stuff. They would they they would do a whole universe of their own particles. They would, and you're right, Shiloh. Like a neutron scattered out of a nuclei becomes a proton again. It stabilizes to this fundamental building block that we know has zero decay. Well, or if
It's a
it
proton
does,
and an
it's
electron. It
extremely
looks a
long.
lot like a hydrogen, actually. It's kind of strange. It's almost like turns
Uh-huh.
into an atom, and that's kind of one way to think. The
Oh,
energy balance isn't quite perfect.
Oh yeah, isn't it like a proton, an electron, and like a little
A
leftover
little
blab
neutrino-y
of
type thing,
something?
something,
Yes.
little something,
Oh,
something.
the neutrino. Yes, it emits an electron and a neutrino, and the neutrino is the part in the equation we couldn't figure out where did that energy came from, so we called it a neutrino. But this is again. What about we're actually observing, as Anastasia was saying, fluctuations of the field in which we're making these collisions, and they're not actually the proton, and so QCD, QED, all, like at the end of the day, this very fundamental particle that makes up everything, that makes all the mass in our universe, like the nuclei of the atom, the proton, is not addressed properly there. And when you bring in 0 point energy and you calculate how much energy in that little cavity, because we have a pretty good sense of the radius of the proton, how much energy in that cavity is going to bounce around and create, a energy value that we can measure, you get exactly its mass. Like that, that's just remarkable.
That is
And
pretty
then
crazy.
and then when you treat that little cavity as the plate of a Casimir effect, right? Then you can calculate the force that this cavity is going to produce because of the external waves are not able to enter that cavity. The Casimir effect that confirmed the 0 point energy, right? So it's two plates that are eliminating some of the long electromagnetic modes of the 0 point energy, enough so that you get, keyword, a gradient, right, in the field. And the result is you get a force on the plates, pushing the plates together. Well, when you calculate that for the proton, so if the plates were the distance of the proton, right, which we can't get plates that close, but so the Casimir force that we measure is that plates are at microns apart, which is a universe for a proton, right? So we get a little force, but we do get a force. But if you bring them close so that they are the size of the proton, then you get the color force. You get the force that you measure in the nuclei of the atom, actually inside the proton. We actually, for the first time in the last 2 years, we've been able to measure the force inside the proton, and it's equivalent to the force inside the neutron star. It's mass. It's a lot, right? And it's exact for the Casimir force. But we don't rely on that in our paper. The paper you have, by the way, is not the one I published. The first version. This is the paper that's in peer review right now. But we don't rely on that. But we find it cute. Comes out, right? It's kind of nice, and then and so now you start to get a sense that you get gradients of electromagnetic fluctuations in the structure of space at the quantum scale, at the very, very fine scale of the Planck regime, at the Planck level. And now you're getting really close to like quantum foam from John Archibald Wheeler, and and now you're starting to see, oh wow, we're living in a field. What happened to physics? We eliminated the field. We just said, oh, everything is independent, and I can make like it's not, interacting with anything. And guess what? Like, Bohmian mechanics tried to put it back in, but that's another story. This whole thing just becomes untenable because you remove the source of energy that's making the thing go. You can't do that. You can't. So when you do that, you actually violate the laws of conservation. Like, it's remarkable. It's
Let me ask.
remarkable.
Can I ask you a kind of a question from a different angle? So, as far as I can tell, like mathematically, this is quite profound. Like, I don't see any issue with the argument that you've presented in this paper from like a quantitative
There's
logic
no
standpoint.
mathematical error.
I don't think there's any. I mean, I'm not a mathematician, but from what I'm looking at, I've tried to tear it apart. I've talked to people. Right, it doesn't seem like there's a mathematical argument gone awry. The problem is getting standard physicists to pay attention to this argument, and they want to write it off. And so I want to ask you, is there an experiment you can imagine, or what would it take to get people in the field who are comfortable with QCD, QED? They're comfortable with this approach despite its internal contradictions. What would it take? Like, can you think of a piece of evidence that would really open people's eyes, or an experiment, no matter how much it would cost, or if you were king of the world? Like, can you think of a way to make this obvious for people who are comfortable with this standard collider structure?
I tell you, Shiloh, it's painful. I just want to say, like, on a personal level, it's painful. It's been painful. I was crying this morning writing about it.
Oh man,
how painful it was throughout my life. 35 years, and not being able to get a year. I have a hard time getting a year from YouTube bloggers, even that are technical. Because I choose to talk about consciousness and other things. But I thought one thing that would do it is a prediction that comes out right, that would and so I've made many predictions. Like, I predicted we were going to find black holes at the center of galaxies, that we're going to find that black holes were there prior to galaxy formation, that predicted many things. They predicted we were going to find a very dense mass in the center of the sun that that's equivalent to a black hole. But and they just, new studies are finding it. But those are pretty out there things. And so in 2012, when I applied what I call the holographic mass solution, because actually you can solve Einstein field equation with Planck oscillators. And I figured that out geometrically early on. And I applied it, and it was giving the right answer for the force and for the mass and all this, but it was giving the wrong answer for the radius. It was 4% too small. And I was like, oh shit, like, why is that? Why is it wrong? It can't be wrong. It was like 10-digit accuracy on everything else. I'm like, no way, it's wrong. And so I had two choices in the paper. I could say, well, my equation is good for everything else except the radius, or say somebody's messing up on measuring the radius. I went for the second option, and I mean, in a nice way. And I don't mean any of this in an arrogant way. I understand like physics is a complex, and people get trained, and I never really mean any harm. But so I predicted the radius of the proton to be smaller. I didn't know at the time there was an experiment in Zurich in an accelerator that was trying to measure protons more precisely.
This is
And
the
you see,
muonic hydrogen experiments.
yeah, that's right. And they made and they publish. I published in December 2012. I mean, I sent it to the Library of Congress. It took a little while before it came out. And in 2000 in 2013 January, like a few months after, they announced they had found a new radius for the proton that was smaller, and it was 4% smaller. You can imagine I freaked out. I'm like calculating like crazy within minutes of seeing the article. And sure enough, I was inside 1 sigma of the experiment. Like I'm inside the margin of error of their experiment. So I'm like, wow, it came out. Like I thought maybe I'll die before they measure the radius of the proton more precisely, and then it created a lot of controversy, and people were saying, oh, but it's because they're measuring with muons. Muons are heavy electrons. They must be flexing the surface of the proton. Da 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 da. It went on and on and on to 2017, where they actually were able to measure it with electrons. And guess what? They realized that the error was because they were applying the standard model to the equations in the measurements. And when they removed that, they actually got the same radius, and they actually changed code data in 2018 to that radius. And to this day, it's the radius the proton. And to this day, it's not fully resolved in the standard model. It really isn't.
So
They
that
say
that
it
that story
is.
is pretty remarkable. I mean, I've heard the argument that there was a 2010 paper that reported this value, but nobody was buying it. Like they reported the 0.84 femtometer
Yeah,
radius back in
yeah,
2010. You
that's
weren't
correct.
aware of that paper?
No,
I take it.
yeah,
Is there any?
I
Is there any like
I
for your
did have.
detract? Like just for your detractors, do you have any like? Is there any paper trail of you working on that idea back before 2010?
Oh yeah, this paper trail all the way back to like way earlier, like a decade earlier.
Because
But
that's amazing, actually. Like I feel like I've seen people write you off because they're like, oh, well, you just back calculated, like you somehow knew about the 2010 result and you back calculated it to fit it. And
yeah, I heard that argument. But even if I had done that, which is wrong. Even if I had done that, it's irrelevant. The fact that I get the right answer with the theory, with the mechanical concept that gives you the right mass, the right radius, the right force, the right everything, like it's irrelevant if I predicted it or not. It really isn't.
I
Like
mean, it certainly points
it
to you being on the right track. Like it is pretty crazy, regardless of, honestly, like regardless of whether you knew about the 2010 results or not. It wasn't a popular result. Nobody thought it was true. Nobody believed it. They didn't update the code data until like almost a decade later.
okay,
Uh,
I'm gonna tell you a story. I gotta tell you. So I came up with the final equation in a very strange way. I was giving a seminar, 11-day seminar in Tulum. Okay, I had like 25 to 30 people for 11 days. It was like 15 hours a day of physics and all the stuff I do and all this, and everybody, and one of the participants was a mathematician. And I had a first version of the paper the holographic mass solution paper, and I was presenting it. And the mathematician in the middle of the talk stopped me and said, "You have a unit problems." I had a unit problems in my equation. Okay, until then, this is 2011. And I'm thinking, oh, and then he comes up to I'm like, come on up, show me. And he comes up to my front and goes, yeah, you got centimeters, the units are wrong. And I'm like, oh, shoot. And I'm like, you're right. Okay, I know I'm on the right track, so I'm going to solve this. And so that night, I finished at 11 o'clock at night, and I stayed up all night, right? Trying to resolve this. So I'm in my bed on my little computer going nuts I'm like, I gotta solve this. I cannot show up in front of these people tomorrow with this unsolved, right? And so I'm like freaking out, right? So I'm like going at it, and I'm I'm holding having to go to the bathroom for like 8 hours kind of deal, right? And I'm just calculating how I'm turning all this stuff around. I've got all my equations, and I'm like, okay, I can't stop. So I'm like going to the bathroom with my computer. And while I'm on the bathroom, I found the answer. But it's 4% smaller than the standard model. And
That's
I'm
awesome.
thinking, shit, that's as close as I can get. I'm going to have to survive. And the sun is rising. I'm going to start, the yoga session with the participant is kind of starting. I got to, I 4% is going to have to do, right? And I go to the talk, and I unveiled the new equation. I'm damn sure the units are good this time. And the mathematician looks at it and goes, wow, 4%. I've seen that somewhere. And he gets on the net and he goes, there's a paper in 2010 that was published that shows a 4. How close are you? And he calculates it on the spot, and he goes, holy shit, you're inside the margin of error of the experiment. And so that was how it happened. So there's plenty of witness.
That's an
awesome.
amazing story.
I mean, it seems like a stupid. I see what you're saying about it. Hardly matters whether you actually had access to that. Like the fact that it conforms to this whole canon of the way that you're thinking about it, I think is pretty profound.
Well, if the paper of 2010 had a mechanism to predict that radius, and I had taken that mechanism in my work to predict the same thing, then it would be different, of course. But it was just a measurement. There was
and everybody thought they were wrong, by the way, too, right? So that everybody,
exactly.
right? That wasn't like a popular idea at all.
No,
it's not something you would be aiming for.
I wanted to ask you about like why it is that you've had such a hard time getting your ideas out into the world. Because like even as we were talking, we were really excited that you reached out to us, and so we started telling people that like, oh, Nassim's coming, and people are like, oh, Nassim, you shouldn't have him on your show. It's going to like devalue the entire process. And
I know.
this
is why bloggers refuse to interview me.
But I feel like there was some period of time where you were like deeply embedded in the esoteric community. And has there been a change in the way that you're presenting these ideas, that you've started to talk more in the conventional language of, mainstream physics, and really have honed how you tell the story in order to make it something that's clearer and more graspable? Or have you been presenting it the exact same way from the beginning, and it's just now that people are starting to realize that you're actually making a really valid point?
It's a little bit of both. I was kind of a victim of the people that wanted to hear it, meaning I had to finance this thing. I mean, my budget in the van was $2,500 a year. Okay, and
Wow, that's
yeah,
impressive.
You got us beat.
yeah.
What were you
Honestly,
eating? Hold on. What were you eating for $2,500 a year? Were you dumpster
very
diving?
little, very little. Actually, I was Breatharian for a while, but this was really part of a evolution, a spiritual evolution for me. For me, there was no separation between the world that I looked at was clearly magic, right? It's clearly, and the fact that I was there looking at it was already like mind-boggling magic. For me, I had no, you see, this is why I studied independently. My father was a scholar. He was one of the top child psychologists. His director of thesis was Piaget. He was the director of the Piaget Institute. He was like, I had seen academia, and I knew, and I was a very strange child, and I had all kinds of issues. I mean, yeah, because I mean, I didn't fit in very well at all, and my father being a famous child psychologist, it didn't jive well, and so I, you know, I studied independently, so I could have complete freedom to study what I wanted, and to go wherever I needed to go, to be able to like, and physics was, I could see how I didn't want to be formatted. I wanted to be able to like think outside, like understand what they've done, where they've come from. And so I studied significant amount of history and so on, and then as well, but I wanted to be able to fly. And so I studied ancient civilization. I studied like all kinds of mysticism. I studied all kinds, like for me, in the 90s, if you went to a physics conference and started to talk about consciousness, there was a good chance they were going to ask you not to come back, right? It was not acceptable. Consciousness was not anything that was rigorous or that was worth studying or anything. You could say the F word, but you couldn't say the C word. And so I didn't want to have that constraint. To me, obviously, if I'm going to be writing the equations, I better know that those equations eventually are going to lead to me writing them. Meaning, you know, you can't just eliminate the concept that consciousness is part of the equation somewhere. It's got to happen somewhere that you got there and you turned around and you looked at the universe and you tried to understand it. To me, that was critical. And so I didn't want limits. And I had to like be able to bring this to the world, what I was discovering. And the people that would listen was the people that had those experiences, whether it was because they took some ayahuasca or mushrooms or whatever at one point, or because they had some natural spiritual awakening or whatever, it resonated with them. And so I was a little bit of a victim of, I got put in the marginal part, and my first papers were a little wonky, meaning they were not rigorous enough. They were, I was making my hand, I was trying to like describe the best I could, and I was getting help from Dr. Elizabeth Rauscher, that was my co-author, and all this. And I was trying to describe this fluid dynamics of spacetime. The first paper I published was, a consideration of torque and Coriolis effect in Einstein field equation, and the origin of spin, and it got censored right away. It was right away censored. I didn't know I had touched on something sensitive. and so it got censored right away. So that put me in a bad situation with the academic structure. And so yeah, and then there was a very aggressive campaign of disinformation about me for years, and I didn't want to do anything about it. And I should have reacted right away, but I thought, okay, well, there I let them do their thing, and it was all over the place. And I'm not a conspiracy theorist. I'm not, that's not my thing. I always give the benefit of the doubt, but literally everything I put out would get trashed right away. So it became, and so I understand it becomes very difficult for other scientists to be willing to take that risk. I literally had physicists lose their job over endorsing my work, get fired, get like students be like having interventions on students that are trying to write their PhD on my work. So it's been a long journey. It's finally relieving. And so you're right. In some ways, I said, okay, well, I'm gonna like try to like partem partem but
Partake?
yeah, no, compartmentalized, like
Oh,
make
compartmentalize.
compartmentalize things a little more, and like keep certain things out of the physics so that it can be more clear. But at the same time, the physics community has advanced quite a bit, and so they're actually meeting me now, more of where I am. There's many things that they're realizing, that are confirming a lot of the things I've been saying for a very long time.
I mean, in many ways, this is a really cool story because you come up with this idea outside of the academy, and you struggle with the thing that I think most people who come up with ideas outside of the academy struggle with, which is like, how do I talk in the language that these people are capable of hearing? And Shiloh and I always talk about this, where it's like, when you go through grad school, there's this immense pressure to learn to talk. Like lab meetings, you either weekly, or you present at them either weekly or like monthly, but you're basically always taking whatever it is that you're working on, you're putting it together into some form of presentation, and then the entire group sits there and critiques the way that you've talked about it, points out the places where things don't make sense. And obviously that can be very, very constraining if you're trying to do something that, is outside the frame of that. And yet there is this level of discourse that people demand of serious ideas. And a lot of people don't get there that are working outside the academy because they feel the pressure from the external forces. And instead of being like, okay, well, I have to figure out how to put this in a language where people will understand and go through this compromise of compartmentalizing and putting one thing here and another thing here and then dealing with them one at a time, I think that engenders a lot of like bitterness and strife inside of people that prevents them from being able to find the language. And so I just think that it's kind of extraordinary that instead of being consumed by that and like reacting against it, you realize that there was great value in, okay, I think I do have a very profound idea. Now, how do I translate it into the language that people will actually be
Yeah.
able to hear? Because like,
Yeah, and how do I get collaboration and support from people that have pieces or that have knowledge of a certain formalism to help me flush out these ideas and present them in an acceptable way and all this, which is something that I'm only in the last, few, like the last decade being able to do. And so it really, and so it took some time, because if you look at my earlier papers, it's not so consistent, because as well, I'm searching, I'm searching, I'm going through the math and trying to find how do I connect to what they wrote. I see it in my mind's eye. I know, that the math should work this way, but I have to like learn their math, first of all. So general relativity, quantum mechanics, quantum field theory and all this, and then put it together and say, okay, you see this thread, you can pull it this way. You see this thread, you can pull it this way. And look, you get something new that's more consistent, right? Which is where we were at in the conversation. But it really kind of like take a lot of energy, a lot of pain. My children suffered from this, um, because of their father, walking around the island in the kitchen, like this for 5 years, and things like that. But but I, I'm like, let me put it this way. I'm so glad, like this morning tears were tears of of pain, of all the pain I felt, but tears of joy as well, because of all of this, like polished the work so that it can be a diamond. It made it what it is, right? It made it what it like, and I want to say, I don't see how, like, and I'm biased 100%, but I'm just gonna say it. If this is wrong, if what I've presented is wrong, then quantum mechanics and general relativity are fundamentally wrong. Because really, what I've done is actually very little new. I just put the pieces that were already there in a different order. And all of a sudden it just comes out, and it's consistent, it's mathematically accurate, and it doesn't require quantum magic. It doesn't require, free parameters. There's no free parameters. There's no like, oh, we got to invent this like crazy thing, or, I got to invent a new field, or, there's none of this. It's just classical, analytical from the beginning to the end. And this is why there's like 70,000 downloads of the previous, how do you say, version of the paper that you have, and there's no comments from anybody. It's crickets, right? It's not like they didn't read it. This is a 50-page paper. You don't just download it. You might view it. There's more views than downloads, but there's still 70,000 downloads, and there's not errors. So, and I mean, we got a beautiful comment from Dr. Melanie, which is a retired physicist from Los Alamos Laboratory that has written the book on quantum electrodynamics. And he said, I don't see errors in this, and it's really interesting what you come up with. And so, that made my heart sing.
That's really beautiful.
Did you publish the first version in a journal? Was there notes that you got back from your viewers or anything like that?
I've been trying to publish that version in journals since then, which is almost 2 years now, or I think 2 years. I've updated the so in the first. So remember, you get the correlation function, you get the mass, the proton, right? And then when you do this, there is a direct relationship to. So I'm going to get a little technical, but you read the paper, so you're going to understand. There is a form of Einstein field equation that was developed by Zeldovich that show that, Zeldovich did the show that like space-time can have memory and so on, and that showed that like when an electromagnetic waves goes through a B field, a charge field, a certain percentage of the energy is converted to gravitational waves or mass, and so when you're describing this field, this 0 point energy, right, that's becoming coherent inside the proton, right? In the nuclei of this coherence, you have high energy uh, events, right? When you calculate these high energy events because of the electromagnetic fields orbiting in coherent way in that region, using those equations, you find that it obeys exactly the condition of a black hole. So you refine Einstein's, and Rosen approach, but showing that it's the energy inside the proton, not the radius, that changes. And when you do that, so now you have a little black hole at the Compton radius of the proton, so it's internal to the proton. You have different phase transition that comes out in the mass. So the math shows you that, like, the nuclei, the very center, is highly coherent, and then it decoheres, and then it decoheres again. It goes through two horizons of decoherence. And when it decoheres the first time, it's exactly equivalent to Einstein field equation. It's exactly equivalent to the black hole. Like, there's no chance that would happen by, this is analytical. This is not, I'm not putting it in. And then it decoheres again through the charge radius of the black hole, and it gives you the rest mass. And so you can calculate this, and when so you say, okay, well, if I have a black hole in the nuclei of a proton, okay, then let's use cosmological physics. I should be able to see Hawking radiation from that thing, right? I should be able to calculate that. So then you calculate the Hawking radiation of a, Compton size, Compton wavelength black hole inside the proton. Guess what you get? You get the rest mass. So now you get the rest mass, the proton. You get the exact value we measured from the radiation, the Hawking radiation of a black hole proton. Like, you've applied cosmological theory to a proton in the nuclei of the atom, and you got the right answer. That's already kind of remarkable. But now you have to consider that the internal correlation function are telling you that you got the rest mass in it too. So that means the vacuum fluctuation inside your oscillator is producing the energy that is being radiated. So you have a source for that radiation. So that thing is stable, massively stable. Like, even if you assume that source of oscillation from the vacuum fluctuation will go away, it will dissipate over time. So in the paper, we do the calculation. You exceed the time of the universe by billions and billions and billions of years, because the vacuum density, even if you renormalize at the Planck scale, is super dense inside that proton. So you got almost an infinite amount of energy, and that's assuming that the stuff you're radiating is not returning to it. That's assuming that it's gone, like that there's nothing feeding it from the outside. It's only what's internal, which is unlikely.
Okay, so
unlikely.
So my next question is kind of a question of, maybe you would bin this as ontology, maybe it's metaphysics, but is the language of black holes the optimal language for discussing this? Like, I
No.
know that it's the historical language, and I know that
Right.
it's what's established, and you don't have to argue with people about the fact that black holes exist, but, like, is there somewhere that you're aiming for that rationalizes this a little bit? Because the black hole is is we talked earlier how you have to be able to see something in the mind's eye in order to work with it. And the
Right.
black hole is kind of the opposite of that, right? It's literally a complete erasure of internal structure, internal models, internal occurrences. It's this like infinitely dense, infinitely small mathematical point. And I'm like, I think that everything that this is pointing to, especially with the Bohmian mechanics. Go ahead.
Yes. No, I'm just saying we're returning to infinities. Just saying.
Yeah,
Right?
yeah, I think so.
Yeah.
And so I kind of want to lead you into this, where I'm like, what is the language that is the next generation of discussing this, that moves away from this kind of, I would say, almost mystical object that is, in your model, both cosmological and nuclear?
Well, I don't know what the terminology is. People fault me for using the word black hole because they say, but you're describing something different. And I'm not, I don't have the liberty to use another terminology because it obeys exactly the Schwarzschild condition or the equations of Einstein's, and so I'm stuck with that terminology. But certainly from these equations in that paper, um, it says that it's not what is described in typically when we're describing a black hole. So there's an historical issue with black hole. So I'm going to tell you the historical issue. So when Einstein wrote his equations, he could not solve them. He could not find the solution to them. They were too complex. He couldn't see how to solve them. He didn't even know if they were going to be solved in his lifetime. Um, and he published it, and Carl Schwarzschild, which was calculating, trajectories on the front of the Russian war, got the paper somehow and solved Einstein field equations for the Schwarzschild solution, and sent it back to Einstein. And Einstein was so glad and so bummed because he was so glad they were solved and so bummed that it predicted an infinite curvature of space-time that he didn't know what that meant. And and the and the thing is that Schwarzschild did it on the back of an envelope while at war. So he made it as simple as he could, which is already pretty complex, the Schwarzschild metric, and made it like a non-rotating, non-charged object. So it's like, I'm gonna simplify to like the thing's not rotating and it doesn't have charge. And it took till the Kerr-Newman solution, the 60s and 70s, till something came out in which Einstein's equation could be solved with the rotating charge object. And even that solution is based on Schwarzschild, right? And so, um, and so all this time, this vision of this point in space that's absorbing everything around it, that's just sucking everything up, and that anything that it's just a monster thing, it's just awful. And that's why Einstein thought this thing doesn't exist. Like, there's got to be a better, way of thinking about this. And his work with Rosen was about that as well. And so the result is we got sold this picture of a black hole that's horrifying. This is a great destroyer. And the fact is that a rotating black hole does not in any way absorb everything that's around it. Actually, things to fall in it would have a hell of a time because the thing is spinning at near the speed of light. Right? And objects accelerate, and there is there's Coriolis forces, there's centrifugal forces, there's all kinds of things that are occurring that are making very difficult for things to fall in it. And clearly, if everything was falling into black holes only, galaxies wouldn't exist because they have black holes in their center. You know, and since they were there before the creation of the galaxy, galaxies, stars, and all this would have never emerged. So, you know, historically, there's this misconception about the nature of black holes. In fact, in astrobiology, it's been shown now that the radiation of black holes are essential for life to develop on planets, even. There's all kinds of evidence that black holes are actually the seeds of creation, not the destroyer of creation. But in the view that's developed in the papers that I'm showing you, that I'm sharing with you, it becomes obvious that 0 point energy, the energy of the fluctuation of the vacuum at the very fine level, the collective behavior of these fluctuations produce the energy that makes black holes. It's not mass falling into itself and you know, eventually making a black hole. It's the source of mass. it's the fluctuation. You have to visualize the vortex rubber ducky thing in the structure of the vacuum structure that's making little vortex at different scales, and we call them black holes.
All right, let's work
And we
on trying to
confuse them.
let's try to visualize that substance, whatever the heck this is. So there's this vacuum structure, and
Yeah.
the way that we've talked about this so far, if I could summarize it, it seems like what you're saying is that there is some sort of standing wave structure which is drawing from this universal sink almost. It's really, there's this 0 point energy, there's a minimum amount of energy that's available from which these nuclei can draw the source of this energy, this pull, this, right, to hold them together, or in the case of gravitation, these amalgamations of lots of atoms that are pulling on one another. But we've kind of avoided like a material representation of that structure to this point. And I understand why you do that.
We got rid of ether. Yeah.
Exactly. So the question, I guess, this is, I don't expect you to have like an answer necessarily, but you must in the back of your mind entertain that there is some material structure which has not been elucidated to this point that is responsible for these interactions at the end of the day.
Something that
I don't understand your question.
Well, so this comes back to what I've been pointing to throughout this entire conversation, which is that we're still talking about forces. Like the foundational feature is an action, right? So like
we're talking about the fluid dynamics of the structure of space.
And
right, so
the forces are emergent from those dynamics.
And so I think
they're
that the question that Shiloh is asking is, he's like, what is your model for the structure of this fluid? Because since the forces are emergent.
Well, like if we take a fluid, like a normal fluid, right? Let's just go with water in the bathtub since we started there. It's got little waters, right? Like individual waters are the actors, and they're enmeshed with one another, and they have tension and they have displacement with one another. And the medium that we're discussing about, that's at the heart of all of this, we've talked about it as an oscillator. It's polarizable in some strange way. There's like, if we...
Not on some strange way, it's because angular momentum is conserved across all scales. So you have angular momentum at that scale, at the Planck scale. I call it a Planck plasma. It's the best representation I could come up with. So think of the particles that makes up the plasma is the Planck scale, is the Planck oscillators, and the collective behavior of these Planck oscillators make particles, atoms, planets, stars, galaxies,
And so do you have a
universes.
Yeah, great.
And
Perfect.
and when you solve this, you get the right answer for the mass of the universe, for the temperature of the universe, for the mass of the galaxies, for the temperature, for stars. You get all the right answer, and you see these fundamental constants that are present across all these scales that defines the scales and the forces that we
Yeah,
measure.
there's no that part is solid. Like I think that the quantitative conversions are really compelling here. I'm just trying to see if we can give material form to the actual structure that's mediating these forces.
like do you have a picture in your mind of the Planck oscillator? Or like how the Planck
Yeah.
oscillator Oh yeah, so like what's your mental picture? So when you think of a Planck oscillator, what does it look like for you? What is it made out
It
of?
looks like the math requires that these things at each scale are toroidal. So it and so they're toroidal. They have radiation and absorption. So they have poloidal vorticity and toroidal vorticity. So there's the
They almost
math
sound
is
like little tiny like subatoms.
right. They're subatoms made of subplanckian structures that are hyperplanckian. So that this is when you exceed the speed of light. This is why you have entanglement in the universe. This is the entanglement is because the wormhole mouth are Planck side. So the information that's traveling through the wormholes are subplanckian. They cannot go through a Planck size mouth. They are subplanckian. So I calculated the subplanckian speeds, the subplanckian, and it all works out. It's just mind fucking boggling. I'm sorry to say, but like I'll give you an example. I'm with the physicists here, the equations you see behind me, like we're calculating. I've got equations everywhere in the windows, and we're trying to figure out how, because now we have a scaling structure, we know what the constants, how they create the scale, so we can scale below the Planck scale. We the Hawking radiation and Einstein field equation have a hyperplanckian problem, meaning at the horizon of a black hole, the speed exceeds c, and so the waveform, and so we solved that because we know how it's scaling. So we calculated, just for fun, we're calculating, okay, so the subplanckian speed, what is it? So we end up with like a speed of like 10 to the 40th the speed of light. So it's fucking seriously quick, right? And so I'm thinking right away, like, oh, that would be the refresh rate for all protons, right? Like Wheeler thought that there was only one electron going around very quick, that kind of thing. So, like, you would have to have a refresh rate. So I'm calculating the refresh rate, and it fucking blew my mind, because when we calculated at the subplanckian speed how long it would take for all the information, if it left one bit left on one side of the universe and went through all the protons and came out on the other side of the universe, and it was 10 to the minus 23 seconds, which I recognized right away. It's the interaction time of the strong force, and it's the time it takes one proton to go around its radius. It's literally like gears inside gears, man. It's like it. I'm sorry, I get
I like
excited,
this. I
but
like this. I like this idea of this like these sub atoms. I think this is really onto something. I'm curious though. Do you think we'll? And I've asked other people this, and I've thrown it around a bunch. We think about it all the time. Is there an experiment in the future, 1,000 years from now, which will ever be able to touch or like see, quote unquote, see these sub atoms? Like, will we ever be able to resolve the sub structure with, because it seems like all of our instruments are made out of atoms, and so trying to touch something that's like
Orders
Well,
of
it's
magnitude
that's like
difficult.
smaller.
gazillions of time. Exactly. There's these
Yeah,
tiny
I mean,
little fibers that the atoms are made out of, whatever the heck that is, or that the space in between atoms is made out of, and et cetera. Will we ever be able to
Right.
directly evidence those? Do you have any hope that there's like, can you imagine
Absolutely.
some sci-fi future where we can see these things?
See them, I don't know, but use them to power our world. Absolutely, absolutely. Yeah, that's the thing. It is like this is not just a nice theory where you can say, okay, well, that's kind of nice. We'll have to see how it comes out. You can. It's a direct engineering path to extracting energy from the same source as the rest of the universe, which we already do. I mean, nuclear power, we're extracting the strong force, right? I mean, that is nuclear power. We just have a kind of like, I call it the male approach to, getting shit done. Like, let's just collide things at massive speed and stuff.
Blow stuff
There's a
up.
way, yeah, blow stuff up. There's a way to actually tickle that stuff out, and actually biomimic what the universe does. If you understand how it does it, I mean, if you realize that you gotta, okay, so we create a gradient between two plates and we get a little force, right? You could say you're extracting energy from 0 point energy in that sense. So people argue, but it's very small. Yeah, but it's there, and it's really small only because you're creating a really shitty gradient. Like, two plates is not necessarily the way the universe would do the job, right? I can think of better ways to create gradients, right? Like maybe angular momentum of electromagnetic fields in a high density plasma, like da 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 da. And so and it and that is the key to gravity
We actually have another
control
friend of the
and to
podcast. Our friend Mike McCullough is trying to instrumentalize those Casimir effects. He's
yeah.
actually, and it's funny because when we first met him, he was pretty down and out about a lot of the work that he was doing, and then all of a sudden, somebody dropped a DARPA grant in his lap, and now he's got a instrument going out into space.
Not only that, but the guy who sent the instrument into space, also a listener to the podcast.
Heck yeah. So
Yeah,
we're moving
yeah.
small little mountains here. I do think that there's a real
There's a lot of
there's a real
people-
change in the attitude towards these things that can happen very, very quickly.
Very quickly, and I just want to say it's not like it hasn't been done. I just want to say, just so we have everything on the table, it's not like it hasn't been done. And yeah,
Well, I think that this is kind of the interesting interplay between fundamental science and technology, which is that, Faraday worked out the relationship between electricity and magnetism and instrumentalized it long before we figured out what electricity really was, because I think that you can
we
probably
still don't know.
Still working on that.
Exactly. And so
still working on.
and so I think that there is this beautiful feature of scientific progress where you can get to a point and you can see something, and without fully being able to explain what is the thing that we're pointing to, you can take the principles, the mathematical principles that you've worked out about it, and then say, okay, well, let's see if we can instrumentalize this. And once you've instrumentalized it, then it's like, well, yeah, you can argue for the rest of eternity about whether or not the verbal description of the instrumentalization is shared, and if one person sees one picture and another person sees another picture. But you can't really argue with the fact, like, if you have a lamp, you can't argue with electricity, like, it's there.
That's right.
I think that that's kind of what you're pointing to.
Yeah, exactly. So I was trying to answer your question in some ways, like, if you create collective, if you create enough collective behavior in the structure of the Planck plasma, you will get curvature of space-time, you will get gravitational events, and you will get energy events. And that will change the world fundamentally. And the theory, well, it's like an engineering path towards it, but you can't do it if you think that gravity is a weak force that's out there somewhere, and the strong force and the color force are another force that's down there somewhere, and the two are completely unrelated. I mean, literally, you take the Planck force, which is not me, right? The Planck force is part of the Planck units. You apply alpha g, the ratio of the gravitational force to the strong force, to the Planck force, and you get exactly the color force. And then from the color force, of course, you apply it again, you get gravitational force because that's how it's defined. But then you can scale in the universe, which is what Carr and Rees did, and that was published in Nature, and you find alpha G coming out, all the way through the scales. And so if you understand that, now you've got your hands on something that telling you the dynamics, right? Because it has to do with angular momentum. It has to do with energy, electromagnetic energy radiation. I mean, fundamentally, if I was going to explain this to a 2-year-old, a 5-year-old, right, or a 7-year-old, I could easily say, think of this fluid that's going away from the object and radiating, right? And this fluid coming back towards the center, right? Like a torus, a poloidal, and that is the gravitational field. So you have electromagnetic fields and gravitational field, and all that's happening because there's angular momentum, because it's spinning, because angular momentum is conserved across scales. And from one scale to the other, you see the conservation of angular momentum producing all these effects. And when you look at the galaxy, and when you do this, by the way, you don't need dark matter, you don't need dark energy, you don't need fudge factors to get the right mass for the universe. All of a sudden, everything kind of resolves.
You've come a long way from the $2,500 a year budget living in the van.
Yes, absolutely.
When we first met you, you were sitting in this crazy looking laboratory. What are you guys building?
Well, we're working on applying the knowledge, the technology, the theory to technology to extract energy. The world is requiring a new source of energy very rapidly, very soon. We have to have new technologies in terms of energy production, in terms of transportation, in terms of environmental impact. It has to happen, and it's not going to happen with solar panel and windmills. And nuclear power plant are not the solution neither. There's all kinds of issues with those, and what's remarkable is when you look at the universe, it's so energetic. It's everywhere. It's nothing. This is what we were discussing earlier. The idea, you see, we all get told very early on, there's no perpetual motion. That's a fallacy. There's actually no such thing as, we see entropy. That's true. We see entropy. But if there's entropy, that means there's entropy. That means there is something that's producing the order for it to go to disorder. And if you try to figure out in the universe which part of the universe is creating the order, the only thing you're going to be able to point to that's creating order is gravity, right? Because brings things together. It produces collective behaviors. The source of low entropy in the universe is gravity. That's not
What
me.
about
That's
what
the
about
way.
chemistry? Like, just what about chemistry and electrodynamics in general?
Yeah. Be more precise. What do you mean by that?
Well, it just seems to me like I mean, just looking around this room, there's a lot of the things that are structured in my room are structured because of chemistry, not just
Yeah.
gravity, including ourselves, our bodies themselves.
Right.
So the
Yeah.
atoms are,
Absolutely.
yeah. So there's a
Yeah.
few ordering principles, I guess.
Yeah, but so like let's do it this way. Let's look at it this way. I think there's a great veritasium on this. Um, I think Derek is going around on the street asking people, uh, what do we get from the sun? And everybody's answering heat. Like and and he asks, so the heat is producing life, and then like so some of the energy is absorbed, and then how much is radiated back? And people say less than what's absorbed because we needed to like make everything work. And then you know clearly that's not the right answer, because if that was true, then the earth would be heating up very, very quickly, and we would have torched a long time ago, right? So we're radiating as much heat as we're absorbing. And so then what is like so how is this low entropy, right, which is the organization of chemistry and biology and all this, how is that happening? Because like what are we actually getting from the sun, right? So we're getting order, we're getting low entropy. This our source of low entropy is the sun, right? But then you got to ask, and by the way, this is the part that's not in Veritasium that most people miss, is that for the sun, the part that it's radiating out is a source of high entropy. It's the low entropy is internal to the sun. It's the gravitational field, right? The electromagnetic field is low entropy for any source. And so basically, so then you're going to ask, well, where did the sun get its low entropy? Well, you're going to get back to the galaxy. You're going to get, back up the scale and eventually get to the Big Bang. And in Veritasium, he does this. And he says, so the only source of low entropy, which is people that have thought about this in physics agree, is gravity. But then there is a fallacy, because even in the video, he doesn't realize he makes this error. He says black hole is the highest entropy you can get, right? Um, and that doesn't work, because black hole is the source of the most strong gravitational field we know. So it cannot be the source of it. It has to be a low entropy source, not a high entropy. And this is because of the way we wrote the equations of the surface of the event horizon of black holes. And because we haven't considered the collective behaviors inside the volume of the black hole. We could get into that, this holographic principle and all the problem with like information, and the the way we treat information in black hole, the evaporation of black holes, and all this, and Hawking radiation. So there's lots there, but I'm just saying we missed a part. This is actually how I solved that equation in 2012. I just considered the inside of the volume, and I said how much of the inside of the volume is interacting with the entropy of the surface. And the ratio is exactly the mass of the black hole.
I mean, I think that this opens at least another 3-hour conversation. There's a ton of stuff that I would love to keep talking to you about.
Yeah, I would love to talk to you more about spin too at some point here if we can get together again. I'd love to come out there you're in Switzerland, right?
Yeah, we're
Yeah,
right beside the border, just like 30 minutes from Geneva, from where I was born, like on the other side, the border of Switzerland, because
nice.
it's a little cheaper on this side.
Uh,
Still have budgets,
I
and
get.
um,
I guess I'm just
and I
saying,
love
like
the mountains.
we go out to Europe, hopefully more often than in the past. We were just there, and it'd be really cool to sit down
Yeah,
with you in person next time we're
I'm
out
so
there. And
bummed I missed
so
you guys when you were
yeah, it's too
here.
bad. Honestly, we should get you out
Yeah,
to the next conference if the stars align and it works out.
I would
It
love
was such a
to.
wonderful experience to get all of these. There's a lot of people I think like you who have done decades of work and have felt really isolated from one another. And it was really beautiful because I think a lot of that emotional pain is healed by bringing these people together who have different pieces of the puzzle. And it was a really profound experience. And I think we're going to do everything we can to keep that series going. So I guess what I'm saying is
Awesome.
I hope that we can meet up in person and keep this conversation going because like Nastia said, we've opened up so many cans of worms and we didn't even get to some of our favorite topics, let alone talking
Yeah,
about
I know.
consciousness, which would be really fun too. But I didn't want to
I
mix it
know.
up with this conversation too much because we want to make sure that
Yeah,
we can extract the physical principles to bring it into our other conversations with
yeah.
physicists. So I guess what I'm
And
saying is
and
I
you
hope this isn't the last time that we get to hang out. And
No, absolutely not. By the way, you guys have an open invitation to come and ski and mountain climb and,
Ooh.
hike and mountain bike and everything whenever you want. We're in the mountains near Chamonix. It's really beautiful. It's
wow.
gorgeous. Really good cheese, really good cheese.
You-
And
Sold.
How'd you know I like cheese so much? I'm mostly
Shiloh's
made out of cheese, it
is
turns
like
out.
90%
I
cheese by
know.
weight.
That sounds
Maybe
awesome,
that's the
man. I think
final theory.
the cheese
The
theory of everything.
transmutation of cheese
Yeah,
into
I
the
think we
universe.
can make it happen, man. I think I really see us traveling a lot more in the future and trying to bring people together. I think that's the whole. We're slowly like figuring out what the heck we're doing here. It's not just a podcast. We're trying to actually bring people together who can unstick a lot of these obvious holes that even people on the inside are kind of recognize but try to ignore. And so, anyways,
Yeah,
I guess to
I just didn't fully answer your question about chemistry, so I was gonna get to it, but basically, you know, chemistry chemistry is not isolated from the dynamics of the nuclei of the atom and the electron, and it's happening at a scale that's larger, but it's the consequence, it's emergent from the dynamics that are happening down there. And if you we scale from the color force to the residual strong force to the gravitational force, but along that we actually scale to the binded voice forces and all this, and so we actually it's in there. And you know what, when we scale like this, yeah, at the Planck scale we don't have measurements, but at the color force, starting at the color force scale, we have measurements. We have measurements of the residual strong force and so on. And we're nailing all of this. I mean, think about it. When you're scaling with alpha G, you're scaling 40 orders of magnitude. So when you're scaling twice, you're scaling 80 orders of magnitude. Okay? And you're nailing the values that are being measured. You're nailing them. Like it's just mind-boggling. It really is.
I think that
Anyway,
it's
that's
really
all.
I think it's really profound, Nassim. I'm really grateful that we've met and that we like my evaluation of these conversations is when I walk away, do I have some piece of information that I've gleaned that makes the world make more sense? And I think that that's what's really valuable about these conversations is that we find people that are trying to fit the worlds together in a way where it becomes a little bit less obscure and mysterious with each conversation. And I
Yes.
just I'm
And
so
cats are not alive and dead at the same
yeah,
time.
exactly. And I'm just so
Exactly.
relieved by it. It just makes me feel like I live in a universe that makes sense. And I always think about Neil deGrasse Tyson at the beginning of his book, Astrophysics for People in a Hurry, has this epigraph, which is his own quote, which is that the universe is under no obligation to make sense to you. And I'm like, if there is an idea that this podcast is set against, it is that. Because the universe
Right.
does make sense and we can make sense of it. And people like you are the ones that are pushing that. And I'm so grateful for the work that you're doing.
We wouldn't exist to even contemplate the possibility of a universe if it didn't make sense.
Right.
Yeah.
We're not isolated from it. We're made from it. We're made of. I was calculating the other day the number of protons in the human being, and I was like, wow, it's more than the number of stars in the universe that we observe, the observable universe. Like, wow, like the intense nature of our existence, the miracle of our existence is, it's remarkable. It's remarkable that we can even contemplate it. And if we can, then I see no reason why we can't understand it.
That's beautiful.
Right on.
Where can
Yeah.
people go to follow your work?
We're at Space Fed, so spacefed.com, and it's International Space Federation, so ISF, and we are, changing the website right now, but there will be a brand new website. We write many articles, commenting on science news, so you can, get the articles and read them. We do voice as well, so that you can listen to them in your car on your way, and all this. And we're, building community and connecting people, and hoping that this stigma that talking to Nassim Haramein is dangerous, and it will, is going away. Like, hopefully, I'm happy to have any conversation with anybody, any physicist, anywhere, in any circumstance. And I think, we're putting stuff out that's valuable in some, very profound way. And I'm looking forward to more interaction. And so please go to our website and interact with us. It's, we're, even if it's criticism, I'm happy, I will just, let's have a conversation about it. Let's figure out the universe together. Let's grow. Let's evolve. We have a beautiful planet. We have to preserve it. And there's children that need our help. There's children that need our help. Like, we have to get past this moment in our evolution. I really feel like it's our job. It's our generation. I'm a little older generation than you guys, but thank God for you guys. I love you guys. Thank God for
We're
you
getting old too, man. Unfortunately.
Yes.
But yeah, let's put a pin in it for today. I think that we need to keep talking, so let's find a way to do that. And
Okay.
we'll put links to your website and at least the older version of the paper we discussed today until the new one comes out. We'll update it. But otherwise, let's
just do it again.
Yeah, let's
great.
catch up again down the line.
Okay,
thank you so much,
sounds
Nassim.
great.
Yeah, thank
Thank you so
Nassim.
much for having me. Thank you for all your courage. You guys are awesome.
It was
Thank you so
wonderful.
much.
Thank you.
Thank you.
All right,
Thank
see you
you.
later. Bye, everybody.